talk about the complex numbers. And one of the major reasons why we need complex numbers is that often we may have a polynomial of the third order in some unknown variable x. Okay, so if we have a polynomial of a cubic polynomial in some unknown variable x, we expect to have 3 different solutions. Okay, and but sometimes we don't find all the roots in the real number space. For this reason, we need. This is one of the reasons why we need the complex numbers, because in the complex number space, the roots, they are always there. We denote the complex number like this, and the real number space, we know how we do it. Now, an example that we can provide here is the following. So, in this example, we have z squared minus 4z plus 5. This is equal to 0. Here we have a P2 in z, polynomial second order in z. And now, if we try to represent this one, this z squared, this can also be rewritten z minus 2 all squared plus 1. Okay? Because this is z squared minus 4z plus 4 plus 1, 5. This is what we get. Now, this, if we try to plot this graph, this is going to look something like this. So here, this is 1, 2. So we have one parabola which is going to look like this. Then we lift this one unit higher. So this is the graph here. And it looks like this graph is never intersecting the x-axis. So it does not have any solution in the real number space. Okay, so we can never find a real number which can satisfy this. But we should have these roots in a complex number space. To find those, we have this equation which is equal to minus b plus minus b squared minus 4ac over 2a. Okay, and here we have minus b, it's equal to 4 plus minus the square root of 16 minus 20 divided by 2, and this is equal to 2 plus minus the square root of minus 4. 16 minus 20, we get here 1 over 2 times square root of minus 4, and this is equal to, again, this is equal to 2 plus minus 1 over 2 square root of minus 1 square root of 4. We go again, square root of 4 is equal to 2, so this 2 can cancel this, and then we get 2 plus minus the square root of minus 1. So this is the initial question that we, the big question that we have to deal with, which is that for a long time, the square root of negative numbers, it was an undefined function. But now, this is what we define here. So the complex numbers, they're defined such as I is equal to square root of minus 1. So in this case, the solutions would be 2 plus minus I. Okay? So here are the solutions of this polynomial. Now, when we deal with the real numbers, what is very imperative for all of us when we use them is our ability to find them where they are in the coordinate system. It can be traditionally, we use a Cartesian coordinate system. If we have, it can even be just a single line from minus infinity to plus infinity, and we try to identify where these solutions are. But now, for the complex number, we do have a system how to determine where these points are. But now, so we have a plane which looks like this, which is called the Argand plane, and here we write down the real part of the complex numbers, and here we denote the imaginary part of these complex numbers. Okay, and here this looks like, for this number that we found, we notice that the real part of 2 plus I is equal to 2. Okay, and at the same time we say that the imaginary part of 2 plus I, this is equal to 1. Okay. So if we have any other complex number, we can see also the following: imaginary part of 3 minus 5i, this would be equal to minus 5, okay? And the real part of 3 minus 5i, this would be equal to 3, and so on. So now, the way to denote, or the way to describe a complex number in a plane, we will do it like this. So the general expression, it will be z is equal to x plus I, y. So x is the real part, which is going to be, let's say here we have 2, and the y is the imaginary part, which is here 1. So if it is here 1, one of the solutions, which is shown here, so this is imaginary part, this is this number 2 plus I, this is 2 plus I, and we have also the other root, which is 2 minus I. 2 minus I, this is minus 1, and 2 minus y, here we have it, okay? 2 minus I, that's good. So, and then it looks like we are using to denote or to find where the complex numbers are on this plane. We are using the principles that we use in Cartesian coordinate system, but we can use also polar coordinates. Okay, so I'm talking about these from now because it is coordinates. So we can talk about the polar coordinates because any point here in this graph, such as this one, we can find what is the projection in the horizontal coordinate system and on the vertical coordinate system. But at the same time, we can determine any point here on this plane as by defining an angle first, angle phi, and also the length of the vector. Okay, so the angle phi, it defines a line which goes like this. Okay, and a specific radius, this creates this intersection point, and we can figure out how a point z can be described. So let's write for now that this z we can define for a fixed r and for a fixed angle phi. Okay, so this is very essential, trying to be able to determine correctly where these points of interest are on this plane. Now, the manipulation of these complex numbers, it is similar to the vectors, because the way to define, so let's assume that we have a complex number which is z1 is equal to 2 minus I, z2, this is 3 plus 2i. So let's have these two numbers. The addition and subtraction of the complex numbers, this is defined as follows. z1 plus z2 is going to be 2 minus I plus 3 plus 2i, and this is all equal to, this is going to be 2 plus 3, this is 5, and then we have plus I. 5 plus I. So this is the summation between these two numbers. The subtraction is also the same, but before we go into that, we can define for any complex number, we define the modulus and the argument. So we define the modulus. Modulus is equivalent to the magnitude of a vector. So if you remember, we used to have questions like this. What is the magnitude of a vector v? And we used to denote it like this. The vector v, it would be a vector which was equal to 1, 3, minus 1. Okay, so this was the vector. And how did we define the magnitude? We defined it here in the class. We said square root of v transpose times v. Okay, this is how we wrote it before. Which means that this would be equal to, so we're talking about the vectors just for a few moments. Okay, what is v transpose? V transpose is 1, 3, minus 1 multiplied by 1, 3, minus 1 again. Okay, so then we multiply them together and we should get a scalar. We have 1 times 1, 1, plus 9, 10, plus 1, 11. So here we have the square root of 11. That's good. Now, we have to define the modulus of the complex numbers. And this modulus, this is defined as, let's try to identify what is the modulus of Z1. The modulus of Z1, it is going to be defined in a similar way like the magnitude of vectors, because this is equal to Z1 complex conjugate times Z1. So Z1 complex conjugate, so this is the modulus. Let's write here the argument. And let's write here the complex conjugate, CC. So Z1 complex conjugate, it is 2 plus I, and Z2 complex conjugate, it is 3 minus 2I. Okay, so, and this is called so for any Z, which is x plus I, y, the Z complex conjugate is defined as x minus I, y. So the real part remains the same, only the complex part, you change the sign. So then we come here and we say, we notice that the Z1 complex conjugate is 2 plus I, okay, times 2 minus I. So 2 times 2 plus I times 2 minus I, we know that A plus B times A minus B, this is equal to A squared minus B squared, okay? So similarly, here we have, this is going to be 2 squared minus B is I, and this is I squared. Now I squared, this is equal to minus 1. So minus 1, we get here square root of 3. Second, okay. So this will be equal to the square root of 5. Say it again.
I squared is minus 1, so 4 minus 1 will be 5.
Plus 1.
No, y plus. Yeah, well, we have a minus there for the formula. It's plus 1.
Okay.
So it's square root of 5.
Yes, that's true. Okay, that's square root of 5. This is correct. This was wrong. So this is square root of 5. And this modulus, which is the square root of 5, we denoted, we write it here. Okay. Now, so this is the modulus, and and you can also always try to construct a similarity between how we find the magnitude of vectors. Now, so let's pick up another number. Z is equal to 3 minus 7I. So what is the magnitude of Z? This is going to be equal to the square root of 3 squared plus 7 squared. Okay, 49 plus 9, 58. So this is we have another Z, which is 2 minus 8I, or plus 8I. The modulus here is going to be equal to the square root of 2 squared plus 8 squared. So 64 plus 4 square root of 68. So this is the modulus. Then we have another definition, which is a very important parameter of the complex numbers, which is the argument. The argument it defines or it determines the angle. So theta, this would be equal to the argument of Z1, which is equal to arc tangent of y divided by x. Okay, so this is how we find the argument. In this case, so arc tangent, this is tangent inverse of which numbers? So what is y for Z1?
Minus 1.
Minus 1 over 2. Okay, so what is an angle which is whose tangent inverse is -1/2. So it looks like y is -1 because it's somewhere here, right? This is -1, this is 1, this is 2. So we are talking about
minus 5 degrees.
Minus 26.56 degrees. Okay, that's good. Now let's pick up the other number. So it looks like, so what did we learn here? We learned that we have a vector which is, or this point, because the point of interest is right here. Let's do it like this. Z1, here it is. This is Z1. And that one is found square root of 5 away from the 0. And the angle here, it is minus 26 degrees. Okay? Now let's find Z2. What is the magnitude of Z2? The magnitude of Z2, what would be the answer? So, what is the magnitude? So, how long is this? This side is 3.
5 units.
Say it again.
Square root of 5.
Well,
13.
Square root of 9 plus 4, which is square root of 13.
so, I think using the Pythagorean theorem, we get 3. So, it's something like this, okay? What about the, so this is square root of 13, okay? And then we need to find what is the argument, arc Z2. This would be equal to the tangent inverse of the y over x. What is y? 2 over 3. So what angle do we find if the tangent is 2 over 3?
Nearly 33.7.
53?
33.
33.7. Okay. 33.7. Okay, so these are the arguments of these two values. That's good. And now we need to define the multiplication between any two complex numbers. Regarding the multiplication, let's take this away. So we learned about the addition, the modulus, the argument, so the multiplication it is simply, let's do this by an example. Okay, so let's do here Z1 times Z2. This is equal to 2 minus I times 3 plus 2I. And this is equal to, so we have two terms, we multiply by another two terms, we should get a combination of 4. So 2 times 3, this is 6. 2 times 2I is plus 4I minus 3I minus 2I squared. Okay? So this is what we get. And then we know that I squared is equal to minus 1. So we don't forget this. And we get 6 plus 2. This is 8. Okay? Plus I. So this would be the multiplication between Z1 and Z2. Is it everything okay? I think that's fine. So this is the definition of the multiplication, and then we have a couple of properties which are the following. When we multiply, the modulus of Z1 times Z2 is equal to the modulus of Z1 times the modulus of Z2. And also, the argument or the angle between a number which is equal to Z1 times Z2, this is equal to the argument of Z1 plus argument of Z2. So here we have a couple of important properties. So in this case, we have to, so we found, let's call this one Z3. So Z3 is a product of Z1 and Z2. And what is the modulus here? The modulus here should be equal to...
Yeah, 65 square root of 65. 64 plus 1.
69, right?
65.
65.
65, right? Okay. We get here 65. Then, if this is 65, let's check if the first property is right. So, what is the modulus of Z1 times the modulus of Z2?
Square root of 5 times 13.
Okay. So,
5
this
times 13.
square root of 5 times square root of 13, we really get the square root of 65. So, the first statement is confirmed. Okay. So this square root of 65 is equal to the modulus of Z1 times modulus of Z2. That one is confirmed. Now, we can also try to find what is the argument of Z3. Here, the argument of Z3, this would be equal to the tangent inverse of the y over imaginary part divided by the real part, which is 1 over 8. So, what angle has a tangent equal to 1 over 8?
7.12 approximately.
So, you're saying 7 over 12?
So 7.12.
7.12, okay. So, then this is equal, apparently this is equal to 7.12 degrees. And this 7.12 degrees, this is equal to the
Yes, it's nearly the same.
Okay, that's good. So apparently this is equal to minus 26.56 plus 33.7.
Yeah, they give 7.14, but approximately the same.
Approximately the same. That's correct. So this is, so here we put an approximate sign, and this is equal to 7 point, what did you say here? I cannot pick it up, 0.14. Okay. So it looks like we confirm also these important relationships between the magnitude and the angles, the modulus and the angles. Now, what is useful here at this stage is to have a look what happens to a complex number if we multiply it with I. So let's pick up if we have Z1 and Z1 is equal to 2 minus I. Let's multiply by I times Z1. What do we get? Can you help me here?
2i
Minus I squared.
Y
Plus 1.
So this is 1 plus 2i. 1 plus 2i. Let's try to draw it. 1 is here, 2i is here. So we get this vector. Okay? So this is I Z1. What is I squared Z1? So we
Minus
must say it again.
Minus Z.
That's correct. That's minus Z1, which is equal to
Minus 2 plus I.
plus I. That's true. This is what we get. So we get minus 2 plus I. We have 1 minus 2. So we get this vector here. So this is I Z1. This is I squared Z1. At this point, let's not forget, this was Z1. And then let's multiply I cube Z1. I cube Z1. This is equal to, let's multiply this by I, which is minus 2I plus I squared. Which means that it's minus 1 minus 2I. So minus 2I and minus 1.
Or we could simply express it as minus I Z Z1. and we already know IZ1.
That is, say it again.
Minus IZ1, and we already know it, the value of IZ1.
You are right. So we know IZ1. So we multiply by -1, which means that this is going to be, this vector, it will be overturned as it is multiplied by -1.
I think that when we multiply by I, the vector rotates with minus 90 degrees.
If each time we multiply by I, yes, we rotate by plus 90 degrees.
Minus, yes, by plus, yeah, correct.
Plus 9. So I4 times Z1, this is equal to I squared times I squared Z1. So, sorry, this I squared Z1, this multiplied by -1, times another -1, which is 1. So here we get Z1. So then here, this was Z1, this is IZ1, I squared Z1, I cubed Z1, and here we go back and we see this is I to the power 4 times Z1. So if we look carefully, by multiplying each time by I, we got an angle of 90 degrees, right? So the rotation by a complex number I, we simply observe a rotation by this specific value of 90. And now we talked about the complex conjugates, and the complex conjugates, they do have some properties. So let's take away this part. So complex conjugates, they have the following properties. If we have Z complex conjugate is equal to what? So this is what we obtain. Because we know that the complex conjugate, all it does, it multiplies by -1 the imaginary part. So we multiply by -1 again, the imaginary part, and we get the same number, right? So this is this rule here. Then we have Z plus Z complex conjugate. What is this equal to? So we get 2 times the real part of the Z. Then 2 minus Z complex conjugate. Actually, we can check them here. So if we add these two, what do we get if we add Z1 with Z1 complex conjugate? So this is Z1, this is a complex conjugate. What do we obtain here?
4.
4. What do we get here?
9.
6.
Sorry.
It's fine. I know well, it's 6. So it looks like this is 2 times the real part because the imaginary part are gone. What happens if we subtract these? So we have 2 minus I minus 2 minus I. What do we obtain? We get minus 2I. Okay? And again, so the real part is lost. So 3 minus 3 is gone. 2I minus, so this is equal to 4I. Okay, so the imaginary part, it is double. So here we get 2 times I times the imaginary part of a number Z. And then here we have something which we don't know very well, but we're going to explain, which is the division between two complex numbers. This is equal to x squared minus y squared divided by x squared plus y squared. Then here we have plus I, 2xi, divided by x squared plus y squared. Now, what is the new piece of information that we have here is, so these are some important properties that we should make use of. But one thing that I want you to remind is the following. Can we divide a matrix B by a matrix A? What do you think?
We can multiply by its inverse.
Yes, but it's not the same thing. So the division is simply, it is not defined, okay? So that multiplication is not defined, so we leave it. The same way, also the division by a complex number, it is not defined again. Now, so it looks like there is a similarity between the complex numbers and the matrices. So some operations which are not defined for those, they are not also defined for the other one. But to explain this, let's consider the division of Z1 by Z2. So here we have Z1 by Z2. This is equal to 2 minus I times 3 plus 2I. This is not defined, but what we can do is we can multiply by 1. So let's multiply here by 1 by the complex conjugate, that is correct. This is 3 plus 2I times 3 minus 2I times 3 minus 2I. So we come here and we see that 3 plus 2I times 3 minus 2I, this is equal to 9 plus 4, 13. Okay? And then we multiply the terms on top. We have 2 times 3. Actually, we know what the product is. It's written somewhere here. So the multiplication of Z1 and Z2, we have it right here. So this
8 plus I.
Thanks. This is 8 plus I. Okay. So this would be equal to 8 over 13 plus I times 1 over 13. So this is how we can solve this problem, because otherwise the division, it cannot be considered. Okay, so this is regarding how we play around with the division. Now let's see another example. Z is equal to Z complex conjugate. This was division. Okay, then we can come up with another couple of other properties of the complex numbers regarding the division, which will be the following. So this was just a representative example, and we can see that the modulus of Z1 over Z2 are equal to the modulus of Z1 divided by the modulus of Z2. Okay, so this is a property which looks like very similar to this one in here. And the argument or the angle which corresponds to the ratio of Z1 over Z2, this is equal to the argument of Z1 minus the argument of Z2. Okay, so in principle, these look like equivalent principles, or because there is a similarity between those. Now, so we are doing these examples, and let's go to another important representation of the complex numbers, which is the polar representation. So the polar representation, as we said before, we said that the important thing about the complex numbers is that we want to locate them. Okay. For a moment I was a little confused. Anyway, let's come back to our discussion. So the polar representation, it's a representation where any complex number Z, this can be described as an R and theta, which in principle, we are somehow already doing it. And in order to do the polar representation, And by the way, polar representation, it is much easier to be manipulated. So we can play around with it. It's way easier. So for the polar representation, we use an important identity, which states that e to the power I theta, this is equal to cosine theta plus I sine theta. Okay, and so this is called the Euler identity. Okay, and then what we can do is that we can multiply both sides of the equation with r, and we get r times e to the power I theta. This is equal to r cosine theta plus I r sine theta. So any complex number which can be somewhere in the Argand plane can be described as the projection along the x-axis plus I times the projection along the y-axis, or the projection along the vertical axis. So let's try to see how or let's do it, well, wait a second. So it looks like Z1, this is equal to what? Can you tell me what is Z1? So Z1, it should be represented as a magnitude times e to the power I theta. So what is the magnitude? Z1, which is this number. How far? What is the R? So this is R. What is the length of this element?
Square root of 5.
Yes, it's square root of 5. And this is e to the power I times what?
Minus 26.
Minus 26. Let me write this minus 26. It is minus 26.56, but let's leave it for now like this. And Z2, this is equal to, similarly, square root of 30. Yes, times e to the power I times 34. Let me write this one 34. 33.7, 34. Okay, so it looks like, how are we going to find Z2 on the plane? We just construct an angle of 34, which is 33.7 here, okay? And then we try to determine all the points which we can draw a circle with a radius of square root of 30. The intersection point is Z2, okay? And now, if we want to multiply Z1 with Z2, what should we get? Let's have a look. So Z1 times Z2, Z1 times Z2. What is Z1? Z1 is square root of 5 e to the power I minus 26 times square root of 13 times e to the power I times 34. Okay. So then we multiply 5 times square root of 13. This is equal to square root of 5 times e to the power. What is 34 minus 26? 8. So this is the product of these, of Z1 and Z2. And if we check the result that we get either here or here, we are going to get the same result. For many, including myself, the polar representation, it is very, very useful. Okay? Allow me to erase this one because these are some principles which we kind of learned. So it looks like now we have this diagram here. I might erase this one, even though it's a beautiful one. But let's take it away for a moment. So it looks like if we are to multiply two complex numbers, what would the first complex number be? Well, it's going to have a radius r1 times an angle theta 1, okay? And then we can have another point here, which is the length of R2, and the angle is theta 2. So what is the product of this number, okay, and this number? The product of these two numbers is equal to the product of the lengths, so it is R1 times R2. So we are going to find a number which is going to be somewhere here. But we need to draw a circle, okay, which has a radius R, where R is equal to R1 times R2. But where on this circle is this number going to be? It should be equal to theta 1 plus theta 2. So on top of this theta 2, we can add another theta 1. So it looks like we're going to get something like this. So this is how we represent the multiplication of the complex numbers. Now, it is easy to see this one when we have the polar representation. That's why we said that this one, it is easy to manipulate. Okay? This is easy to manipulate, and at the same time, it is also easy. So let's do the following. We say Z1 times Z2, this would be equal to R1 e to the power I theta 1 times R2 e to the power I theta 2. And the product would give to us R1 times R2 e to the power I theta 1 plus theta 2. So this is the product of two complex numbers. The division of two complex numbers, it's also using the polar representation. It is very useful. So we have here R1 e to the power I theta 1 over R2 e to the power I theta 2. This is equal to the ratio between R1 and R2 times e to the power I theta 1 minus theta 2. So we said that the division by complex numbers, it was relatively difficult, but we don't care. In the polar representation, it is relatively simple to figure this out. So now it looks like so far we are constructing a model of how we can view how we can understand the rotation in the complex number space. Okay. Now let's try to draw another diagram, and let's consider for a moment. Let's think for a moment. Okay. Let's consider a matrix A, and this matrix A, it is equal to 1, 1, 1, 1, minus 1, 0. So we are skipping for a moment the complex numbers, and let's go back to linear algebra. And let's also remind ourselves once again. So each time we multiply with the complex number, we are doing a rotation, right? And how much are we rotating the system? If we are multiplying Z1 with Z2, how much are we changing the angle? Can you see that?
Some of the angle.
Yes, by theta 2.
That's true. It is theta 2. What happened when we multiply the number by I? We rotated it by pi over 2, right? We rotated by 90 degrees. You remember, we had the schema here. We multiplied by I, we rotated by 90, another I by 180. I cubed, it was a rotation by 270. So these were what the complex numbers were doing. They were rotating the numbers. And now, that is something beautiful about the complex numbers, because they do not diverge to infinity. Let's think first of all about this number, 2. What happens with 2 to the power n? 2 to the power n, if it is something like 2 to the power 10, this is a number which exponentially increases very fast. What about I to the power n? What is this? This is an oscillatory function. Okay, because I to the power n, this is going to be I, then it's going to be minus 1.
Minus I, then 1.
Then 1. And then what? I again, minus 1. Okay, so this is, and what is I? I itself, this is e to the power I times 90. Okay? What is minus 1? Can you conclude what is minus 1 here?
E to power I 180.
That's correct. So it's good if you write this actually. So I, where is I? I is a number which will be right here. So this is I. Then what is I squared? Minus 1. So I is equal to e to the power I 90. Minus 1 is this vector. This vector is minus 1, which is equal to e to the power 180. What is minus I? Minus I.
The angle is now 270.
That's correct. We can also consider this angle as e to the power minus I times 90. So this angle is 270 or minus 90 degrees. What about 1? What is 1?
e to the power I times 0.
That's correct. Times 0. I don't know. Куш води да не се кемис и не observe.
Terence.
Terence, okay. But this one, Terence, we can write this also e to the power I times 2 pi. Right? Would you agree with this?
Yes.
Okay, Terence, but what about this? Can you write that 1 is equal to e to the power I times 2 pi times n, where n is an integer number? Would you agree with this?
Yes, indeed, because it will be equal to the power of e to the power 2 pi to the whole number to the power of n.
Yes, so if we rotate by an angle of 2 pi, we start from 1, we go to 1. We rotate again, we come here. We rotate another 2 pi, we are still at 1. We rotate another 2 pi, okay, you always get 1. We keep rotating 2 more pi's, this is what we obtain. But it is important for us to easily determine how we can write down any complex number as a function of these. And then if we can do that, we know that I to the power n, what is this in fact? This is an oscillatory function. This is an oscillatory function. Oscillatory functions, they are good to work with. They are bad because they never converge. But these numbers, this is scary, this is bad, because it exponentially increases, and that means that it will diverge to infinity very fast. But these, they are good. And now, these are complex numbers, they are oscillatory functions. We often denote the phase. So some information, whenever we have a phase, phasa, then we need to use the complex numbers, and you are going to see the use of complex numbers a lot in courses like signals and systems, where you will be asked to take the Fourier transform and similar transforms. Now, whenever you go in the future years and you see that you will be told to calculate the Fourier transform of a specific function, you can do that using linear algebra. Because matrices or linear algebra, they can do anything. So you can describe the Fourier transform, which is a linear transformation in a space to another. You can use matrices. And this Fourier transform, this is spelled this way. We call this Fourier transform. And for the Fourier transform, you're going to need the I. But now, let's come back to our problem. Let's assume for a moment that we are starting, we have a vector which is 1, 0. Let's have a vector x, 0, and see what happens if we multiply a with x, 0. So here, this is 1, 0. Can you help me here? What do we obtain here?
1 minus 1.
1 minus 1, okay. Where is 1 minus 1? 1 minus 1, it looks like we're going to get a vector like this. So what is this? This is x0. The next vector is a times x0. Okay? And then let's multiply a squared times x0. X squared times 1, 0. What is this equal to? This is 1, 1 minus 1, 0. We multiply with 1 minus 1. Would you agree here? So we want to rotate this vector from 1, 0 twice. We did it initially, we got 1 minus 1, so what do we obtain here? What is this? Would you agree here?
0 minus 1.
Yes, 0 minus 1. Maybe we can use a different color here. So this other vector, this is a squared times x0. That's good. So let's multiply this one again. So let's get 1, 1, minus 1, 0. Let's multiply with 0, minus 1. And this is equal, what is this?
Minus 1, 1.
Minus 0.
Minus 1, 0.
0. Okay, is it true? Oh, it looks like yes. Minus 1, 0. Where is minus 1, 0? It's this number right here. So it's going to be this vector. So this is equal to a cubed times x0. So this is a to the power 3 times x0. Because we know that whenever we multiply by a matrix A, we are rotating the vector, and we might also be changing the direction of the vector. Let's keep multiplying. Here we have 1, 1, minus 1, 0, times, we have minus 1, 0, minus 1, 0. What is the result here?
Minus 1, 1.
Minus 1, 1. Where is minus 1, 1? Minus 1, 1. It's a vector which is going to be somewhere here. And this vector, this is a to the power 4 times x0. Okay? Then we keep doing the once again. So we have 1, 1, minus 1, 0 times minus 1, 1. And this is equal to, what is this?
0, 1.
0, 1. Where is 0, 1 here in the graph? 0, 1. So this is 0, 1, and this is equal to a to the power 5 times x0. We keep doing this again, and we get 1, 1, minus 1, 0, times 0, 1. What do we get here?
1, 0.
1, 0. So this 1, 0 is the initial x0. So this is equal to, this is a to the power 6 times x0. We got x0. Because we rotate this vector again, and we obtain this vector here. Would you agree here? So that it looks like this x0, this is equal to a to the power 6 times x0. So one thing that we can kind of conclude here is that is the following. So we can see that here we got 1 minus 1. Here we got minus 1, 1, right? You see what happens here? This result is multiplied by minus 1. What is happening from this vector to here? You multiply by minus 1, right? So multiplying by minus 1 is like rotating by 180 degrees in the Cartesian coordinate system. Also similarly, what is happening between this vector and this vector? You are still multiplying by minus 1. Okay? So it looks like the a to the power 3, so here we have a to the power 3, it's equal to minus identity matrix. So this is equal to minus 1, 0, 0, minus 1. Okay? This is a to the power 3. What about a to the power 6? What is a to the power 6? So this can be thought as the identity matrix. So it looks like the a to the power 6, and by the way, we can also, now that we know this language of complex numbers, we can also assume the following. This is e to the power I times pi, okay? And this is equal to e to the power I times 2 pi. Would you agree here? Because you can see that this number multiplied by a cubed, we got negative sign. This number multiplied by a cubed, 1, 2, 3, we get a negative sign. And you can also see it from here. So you started with x0, which is this vector. You rotated it by an angle of pi over 4. Okay, no, yes, pi over 4. And then what was the next angle? So pi over 4, then pi over 2, plus pi over 2. Then pi over 4 again, plus pi over 4, plus another pi over 4, plus pi over 2. So what is this whole thing? This is equal to 2 pi. Okay? But on average, how much does the matrix A rotate the vectors on average? So it looks like, on average, we are going to rotate the vectors by an angle of 60. So if you multiply 3 times, 60 times 3 is 180. So multiply by -1, or this is what we observe. Okay? And now, let's have a look at do we need these? Let's take them away for a moment. So this is the matrix A, but let's try to find what are the eigenvalues of A. How can we find the eigenvalues of A? Eigenvalues of A, we follow the procedure, which is 1, 1, minus 1, 0, minus lambda, 0, 0, lambda. And this is equal to 1 minus lambda, 1, minus 1, and minus lambda. Okay? So this is what we have here, and we should write the determinant of this matrix should be equal to 0. So we write here lambda times lambda minus 1 plus 1, this is 0. And then we obtain a polynomial of the second order, which is lambda squared minus lambda plus 1, this is 0. Okay? And then we use the same procedure, which is minus b plus minus b squared minus 4ac divided by 2a. So the eigenvalues here, we get that one of the eigenvalues...
1 plus minus square root of 5 over 2.
Square root of 5, let's check. So lambda 1, oh wait, let's do it like this. So this is minus b, what is minus b? It's minus, it's 1, plus minus b squared, it is 1. Minus 4, this is square root of minus 3. Would you agree?
Yes, right.
Okay, so lambda 1 is equal to 1 over 2 plus I square root of 3 over 2. Okay? And lambda 2 is equal to 1 over 2 minus I square root of 3 over 2. So, what are these numbers? They are complex numbers, but if it is a complex number, what is the angle that it can rotate? Now, if we look at this definition, at the Euler identity, let's have a look here. If this is some cosine, which angle has a cosine equal to 1 over 2? Can you use your calculator? Well, and you can try to determine this.
From 45 degrees.
45, no, it's not correct.
60.
60, that's true. What about the sine square root of 3 over 2? Which number has a sine square root of 3 over 2?
Once again, 60.
That is correct. Plus I sine 60. And this is equal to cosine 60 minus I sine 60. Okay? Which means that the lambda 1 this is equivalent, so I don't have space to write it here, but one can interpret this lambda 1 as e to the power I times 60. Why is this? Because we have this identity, Euler identity, right? And lambda 2, this is an eigenvalue, which is e to the power I minus 60. Okay, so it looks like the rotation, we have a matrix A, which is equal to this 2 by 2 matrix, 1, 1, minus 1, 0. Apparently, this is a rotational matrix. So whatever this rotational matrix can do on any vector on the Cartesian coordinate system, this can be equivalently done by the eigenvalue lambda 1 and eigenvalue lambda 2, because they simply represent a rotation of 60 degrees. So if you multiply 6 times, that means that you rotate 60 degrees times 6 times, so we get 360. Is it clear? Okay, so then we can move to a different problem. So this equivalence between the matrices and the eigenvalues, it is essential. It is also very important. And now allow me to take this away because they don't have too much fundamental information. So let's use this part of the board. Okay, so we have some theorems, well, one which is called, so you expect some French. So we have some French theorems because Fourier or complex numbers, they were products of the French mathematicians, P or, okay, and Euler, I think Euler, he was British. So we have also some British contribution next to some French contribution. And here, in this theorem, we can make use of the polar representation a lot. So what is e to the power I theta to the power m? How can we describe this? This is e to the power I times m theta, okay? So this means that we have a rotation by the name of theta, we do this n times. This is equivalent to saying that we are rotating by the name of n times theta, okay? So this is what we can make use of, but at the same time, we know that e to the power I theta, what is it? It's cosine plus I sine, right? So we can write this one cosine theta plus I times sine theta. This expression to the power n, this is equal to
Sine n theta plus I sine n theta.
That's correct. This is correct. So plus I sine n theta. Okay. So here, and we can use this one to solve polynomials equations. We can use this one to solve to find trigonometric identities and many more. So let's see an example. Let's assume for a moment let's substitute here. So this one we read it from here, this one we read it from here. So let's write for a moment what is cosine 3 theta plus I sine 3 theta. What is this expression? We can write this one as cosine theta plus I sine theta all to the power 3. Okay, so this is all to the power 3. So then what do we need to do here? We remember some identities which go like this: a plus b all to the power 3. This is equal to a cubed plus 3a squared b plus 3a b squared plus b cubed, right? So we use this identity here, and let's see what we obtain. So we have cosine plus I theta, etc. So let's write first a cubed. This is cosine cubed plus 3a squared, which is 3 plus 3 cosine squared times b, which is sine theta, but we have also an I, so we have an I over there, because b has an I, plus 3ab squared. Now, b squared, this is the I, it would be a minus sign, so we can put here minus, wait a second. So let's write this here. It's going to be minus 3 times a, this is cosine theta, times b squared. B squared is sine squared, so this is sine squared, plus b cubed. B cubed, it's equal to I squared, sorry, this is I squared times I times sine cubed, because this is I cubed. So this is I squared is minus 1, so we're left only with one I, okay? Like a cycloid, but not one I, square root minus 1. Okay, so we move ahead like this, and then what we can do is that we know that for any identity which looks like this, what we should get is that the real part, which is, this is a real part here, this is another real part, this has a complex term, here there is another real part, okay? So this identity, we know this already, so we can erase this one for a moment, and then we can find that the cosine 3 theta, because we know that this is going to be cosine 3 theta, this is equal to cosine cube theta minus 3 cosine sine squared. Okay, so this is one identity which, wait a second, which we have known this for a long time, and instead of this, this is also equal to 4 cosine cube minus 3 cosine theta. Okay? 4 cosine cube minus 3 cosine theta. Because in order to do this, 4 cosine squared. So this is an identity which we already know this one. If you look at the tables, when you use, for example, the different properties in calculus, you might use these, but it looks like from these, the Moivre theorem, we can use this property to derive how the cosine 3 theta depends on cosine theta and sine theta. Wait a second, maybe I have it. Okay, so this is true. And similarly, we can also denote that the complex parts, which is this term, and this term here, they should be equal on both sides of the identity. So here we can say that sine 3 theta, this is equal to 3 cosine squared sine, 3 cosine squared sine, minus sine cubed. These are all theta, so it looks like the sine of 3 times of an angle theta is equal to these, and this can also be written as 3 sine theta minus 4 sine cube theta. So it looks like deriving these properties, in principle, it may be a little difficult, but using the polar representation of e to the power I theta, we can easily derive these. Okay. Now, another interesting exercise, it could be the following. So, we said that polynomials of the, I think we might have solved this example before, but imagine for a moment, z to the power 6 is equal to 1. So, find the roots. What are the roots of this polynomial? We should get 6. So we should get z1. So can you help me here? So what could be the acceptable roots for z?
From the real numbers, 1 and minus 1.
Okay, so we have here 1. We have also the minus 1s, so it's 1 minus 1. Where are the 4 more roots?
In the imaginary thing.
Actually, the solution most probably is on the board. Not most probably, it is on the board. Can you see it? No, I can't. Do you? You cannot see each other. So, where is the solution of this polynomial? Okay, that is the solution. And now let's see for a moment how this could be the solution of this. So let's see the following. We have here z6. This is equal to 1. But 1, Terence, I think it was you, Terence, that you were asked. We don't. What was 1? 1, it was equal e to the power I, 2 pi times n. Would you agree with this?
Yes, but there must be some real number, not necessarily just.
No, n is an integer number. N is an integer.
But if it is an integer, we can denote it like I to the power of 60. I60, sorry.
So let's write this one. Z, let's take the root of 6. Let's apply z to the power 6 to the power 1 over 6. Then we get the following. This is equal to exponential of I times 2 pi divided by 6 times n. Okay?
Right, so n must be some multiple of 3.
Yes. Well, okay.
Professor, I think for the real numbers, we take n as 1 and n as 1 over 2 for the real numbers.
No, it should be an integer. N is an integer. So, what 2 pi over 6? What is 2 pi over 6? Well, it is 360 divided by 6. This is 50. So this is exponential of I times 60 times n. Okay? N is equal to 0, 1, 2, 3, 4, 5, 6, and more. Okay? So what is this z if n is equal to 0? So if n is equal to 0, what is z?
1.
Yes. So this is, let me write it here. So this is when n is equal to 0. When n is equal to 1, if n is equal to 1, what is z2?
1 again.
If n is equal to 1, this is e to the power I60. Then the next solution, when n is 2, z3 is equal to e to the power I120. Okay. Z4, this is equal to e to the power I180. So this is n equal to 3. Z5, this is equal to e to the power n4, 240. This is I 240. This is for n equal to 4. Okay. Z6, this is equal to e to the power 300. E to the power I 300, which is for n equal to 5. Now, if we use Z7, what is Z7?
We don't need it because we only need 6 solutions.
That's true, but Z7 will be equal to Z1 because these are complex numbers and they don't explode. So they oscillate, but I can write it here for elegance. This is Z7, this is e to the power I times 360, which is also 1, okay? Which is actually this the first solution. So here we have all the solutions of this sixth order polynomial. And let's try to show them here. So the solutions in this graph, they are 1, this is 1, then we rotate by an angle of 60, we rotate another 60, we rotate another 60, we rotate another 60 here, another 60 here, and we come back to here, okay? So all the roots of this polynomial, they lie on a circle with a radius 1. And here we have 6 of those, 1, 2, 3, 4, 5, 6, okay? And these angles, this is 60, 60, 60, 60, 60, and again 60. Okay? So, similarly, we can also identify what are the roots for another polynomial, which can look like this. Z to the power 8 is equal to 1. We need 8 different roots, and you can work out this example and try to find 8 different roots. Okay. Do you have any question? If not, we can have a short break